Okay guys, welcome to the online digital classroom. Hopefully this is all going to work out quite nicely for us. I've set up a PowerPoint that we're going to work through just now, and then I'll have some worked examples on what we're going to be talking about. So to start with, we're going to start thinking about why don't humans fly? And it's not a case of we're not magic or anything like that. Unfortunately, supernatural things like that don't happen to us because the order of nature would be that everything will be attracted towards the centre of mass that is the Earth. So the real reason that humans don't fly is gravity. Okay? But it was an interesting wee thought to think about at the start there. So today we're going to talk about what gravity is and how it can help us. We're going to explain what gravity is and state the value of little g on Earth. Okay, now little g is going to become really important, okay, as we go through these calculations that we're going to be learning about today. Another thinking point for you. If each of these people were supergiant, as they appear to be, and all dropped a stone from that point, which way will it fall? Most of you are probably thinking downwards, but interestingly for two of the people, downwards is completely the opposite direction. But it does indeed always fall towards the centre of the Earth, and that's really important to note, that the centre of the Earth is what everything is attracted towards. So the pull force between those masses, okay, it's called the force of gravity, and it's pulling everything together. It's a force which pulls, okay, and that's all we need to know about just now. We're going to expand upon forces eventually, but for now, all you need to know is there's a pulling force of masses pulling together, okay. The force of attraction between you and the nearest closable person to you is still there, but it's tiny because the amount of mass required to create a really strong gravitational pull is a lot, okay. The Earth has a fairly big gravitational pull, but it's not as big as, say, Jupiter, because Jupiter's a lot bigger than we are. Okay, and a region of space where you experience that pull force is called the gravitational field. So Earth's gravitational field exists around it, and it's not until you can escape the gravitational field of Earth that you can actually be considered as having left the Earth. Okay, so every object on Earth that is dropped will fall to the ground with the same rate, this gravitational field strength. Okay, now on Earth this is what we call 9.8 newtons per kilogram, the gravitational field strength, which means every object that falls accelerates towards the ground at 9.8 meters per second every second. Now this point, I want you to pause this video, okay, and I want you to go and watch the other YouTube video that's listed in the clip, which has Brian Cox going to NASA to test the dropping of a bowling ball and a feather, okay, because that will show you that there is indeed this drop of everything falling. If you can remove air resistance, everything falls at the same rate. The real thing that changes it is that other air resistance friction thing that goes on to slow things down. Okay, but for our calculations, Earth has a gravitational field strength of 9.8, which is pulling everyone down. Okay, 9.8 newtons per kilogram. Every planet has a different gravitational field strength, and it's all dependent on the size of the planet and the makeup of the planet that gives you this gravitational field strength value. Okay, so the Earth has a mass of 5.978 times 10 to the 24 kilograms. Now I've written that all out for you so you can get a picture of just how many zeros that is. Okay, it's absolutely massive. We don't have a mass anywhere near that, and therefore we're not as attractive as the Earth is. Okay, but objects with mass pull on other masses, and the bigger the mass, the more the pull. So Earth has a much bigger pull than Pluto or Mercury, because these are much smaller planets. Okay, and so what's important for us is the mass on Earth causes this gravitational field strength. Okay, now mass is how much matter makes up something. Okay, and it's always measured in kilograms. So you have mass that makes you up, right? But this is where we have a common misconception in the world where we use the term weight incorrectly. Everyone will say, oh, what do you weigh? What do you weigh? You don't actually then answer with your weight, because someone asks me what I weigh, I will tell them 122 kilograms, but that's not my weight, that's my mass. Okay, so scientists are really at odds with the rest of the world because we use mass in kilograms and then they misuse the word weight. Okay, and what we're going to do now is we're going to talk about what weight actually is. Okay, and weight is a force. Weight is the force acting on an object due to gravity. It's the force caused by gravity on anything on Earth or on any other planet with a gravitational field strength. Okay, the unit of weight is newtons, and that's the unit of all force. It's newtons, big capital N, newtons. Okay, now in physics we calculate the weight of an object based on a calculation, an equation. I'm sure you saw this coming because we like to describe everything in equations in physics. So here is what our equation is going to look like. W equals m times g. So the weight is equal to mass times the gravitational field strength of the planet or moon that the object is on. Okay, because the moon is a much smaller mass than the Earth, but still has a gravitational field strength. Okay, and that's why people can land on the moon without floating off. But the gravitational field strength being weaker on the moon is the reason that they can jump around on the moon and sort of take huge, giant leaping steps, because they're not as pulled as back to the ground as quickly as they would have been on Earth, and their muscles are designed for Earth's gravitational field strength. Okay, so we're going to do some worked examples on this. We're going to do some calculations together. You're going to get to see me stitch together a video with some video editing software, make this work out, so hopefully it'll all work out quite nicely for us. And then I'm going to set you a task this week where you're going to be answering some of these questions and maybe researching the weight on a planet or something. I've not fully worked out what you're going to be doing after that, but there will definitely be some questions practicing with this equation. Okay, so good luck with those, and I'll see you in a second for some calculation practice. Alright guys, so by now you'll have watched my video, first half of this video, where I explained to you what weight was. And hopefully you've watched the Brian Cox video, where he shows you the bowling ball and the feather falling at exactly the same rate. Hopefully you're keeping up with all of this. This is just our first chance at looking at a digital classroom, and hopefully as time goes on this will develop into a much more workable system. But this is how I'm starting this to see how it works. So feedback on this would be great as we go along. So we're going to do a couple of calculations, and we always do our calculations in a specific way, and you're probably sick to death of me saying this, but I need to keep reiterating it because your working is so important in physics. So the first thing we're going to do in this is we're going to write down what we know. So the question's asking us for the weight of a 20 kilogram rucksack on Earth. Okay, so that means it's given us the mass, which is the 20 kilograms, and it's said that the rucksack is on Earth, so we can work out this G using our data sheet over there. Now I've stuck that in for you so you've got access to it there, but the data sheet's also on every SQA past paper, and you can get it directly from the SQA website, but it's right there for you to use for these calculations that you're going to be doing this week. Okay, so we know that the gravitational field strength on Earth is 9.8 newtons per kilogram. Okay, now our equation is W equals mg, where W is the weight, m is the mass, and g is the gravitational field strength. So we're going to do 20 times 9.8, and that is going to equal, calculators at the ready, 196 newtons. Okay, we're then going to come down here for the second worked example. Okay, now this says that the lunar module had a weight on the moon, okay, so that's a key point, of 26,000 newtons, and 87% of that was its fuel. What is the mass of the lunar module on the moon? Okay, so writing down what we know that W is 26,000 newtons, and G, if we go to our list here, G on the moon is 1.6 newtons per kilogram. Okay, so writing down what we know, we're ready to go. W equals mg. Substitute in the values we know, so we know 26,000 is equal to m times 1.6. At this point we're going to have to rearrange the equation, and so it's times 1.6 on this side. So if we change side, change operation, we're going to have 26,000 divided by 1.6 is equal to m. And so therefore m is equal to, in your calculator, 16,250 kilograms. Okay, you're ready to go. These are all up on the OneNote, these examples, so if you need to come back and look at them without the video and you just want to have a read through them, they're all up on the OneNote, so you can jump on and have a look there. As it is now, you are good to go, and enjoy the work that I've set you for this week. Good luck. Catch you later.